So my talk is about parameterized inapproximability. So most of the hardest result of approximation only rules out a polynomial time algorithm. So in this talk, I want to show that ETH can be used to reveal the existence of exponential time approximation algorithm. And our starting point is the maximal k-subset intersection problem. So we are given a collection of subset over a finite set of n elements. And the goal of this problem is to select k distinct subset from this collection and with the maximum size of intersection. And another formulation of this problem is to given a bipartite graph, G A in unit B, and we want to find a k vertex set of A with maximum number of common neighbors. So we try to find a maximum by-clique with a fixed number in its left side. Okay, so this problem is NP hard, and we can solve it in n to the power of k by brute force searching. So the question is, can we do better than this brute force searching? In particular, can we find an FPT approximation algorithm with a ratio r? By an FPT algorithm, I mean the algorithm runs. The running time of this algorithm is f of k times polynomial of n, and our approximation means that it returns a solution whose size is 1 over r times the optimal one. So in the literature of approximation algorithm, we always consider polynomial time algorithm. So if we restrict to polynomial time approximation algorithm, then the answer to this question is no under some hardness assumption. So it is not difficult to see that if we have an approximation algorithm for the maximal k-subset intersection, then we can use this approximation algorithm to solve the mass by-clique problem or maximal edge by-clique problem by going through all the possible value of k. So all of these results are based on the PCP theorem, and it produces an optimal instant with a large number of k. So it does not rule out approximation algorithm in FPT time. So why is it so difficult to showing parameterized inapproximability result? Because the reason is most of the proof in classical approximability relies on the PCP theorem, and reduction based on the PCP theorem always produce instance with an optimal solution of large size. For example, the parameter k in this instance may be a polynomial of n, and in parameter complexity we assume that k is very small. It should not depend on n. So the main result of this talk is to give a FPT gap-producing reduction from k-CLIQUE to the maximal k-subset intersection problem. In particular, given on input n vertex graph G and a small integer k, we can construct a bipartite graph H in polynomial time such that if G contains a k-CLIQUE, then there are S vertex in the left side of this bipartite graph with a large number of common neighbors. And otherwise, every S vertex of A, S vertex set of A has very small number of common neighbors. And we know that there is a huge gap between these two terms. And here S is is equal to k choose 2 is the edge number of a k-CLIQUE. So our reduction does not use the PCB theorem, and in fact, it is based on some extreme combinatorial construction. So it applies in a case with small value of k. So let's see what we can get from this gap. So an immediate consequence is to use the n to the power of k lower bound of the k-CLIQUE problem under ETH, and recall that our reduction is from k-CLIQUE to maximal k subset intersection, and we increase the parameter from k to k choose 2. So we have n to the square root of k lower bound for approximation algorithm of this problem with ratio with such ratio. And we can by duplicating the vertex in the bipartite graph H delta times for some fixed delta, for some fixed constant delta, we can obtain a variant of our main theorem, where the S vertex, the S vertex is replaced by S multiplied by delta, and then we can get an inapproachability result of maximal k subset intersection with a trade-off between the approximation ratio and its running time. So it seems that if we want to rule out a larger approximation ratio, we have to sacrifice the lower bound of this running time. And of course, there's okay.
You use only the exponential time for this?
Yes. Yes. You only exponential time hypothesis. So there's no reason to restrict the delta to be a constant, and for example, we can set delta to be 2 to the power of k over s, and then we have a gap reduction from k-CLIQUE to 2 to the power of k subset intersection, right? And then we can obtain the corresponding lower bound with n to power of log k and to the ratio, the log k roots of n. So far, we have seen a gap producing reduction and some simple consequence of it under ETH. So a natural follow-up question is, what can we do with this gap? So can we derive some inapproximability result of other natural parameter problem based on this gap? In particular, we want to find some gap-preserving FPT reduction from the k subset intersection to k-CLIQUE or to k-dominating set. So first, let us try k-CLIQUE. So we want to find an FPT algorithm A, and such that on input a bipartite graph H, you construct a graph G, satisfying if there are S vertex in A with large common neighbor, then G has a clique of G of K vertex. And if every S vertex in H has a small number of common neighbors, then G contains at most G of K over 2 clique. So we want to know if there is such a gap preserving reduction. And a naive idea is, so here we have a bipartite graph H. We use the color coding technique to to color the vertex set A with S color, and we color the vertex set B with, say, 2 times k plus 1 factorial different color. Then we add edge between vertex in A with different color, and we do the same thing for the vertex in B. So it seems that after we add this edge, after we color this vertex and add the edge between different vertex between vertex with different color, then in the case 1, we have a S vertex set with large common number of with large number of common neighbor. So we have a S plus 2. We have a clique whose size is close to 2 times k plus 1 factorial. We assume that also S is equal to k choose 2, so the size is dominated by this term. And in the second case, it seems that the largest clique of H is close to k plus 1 factorial, right? Okay. So this argument is not correct, because there may exist, in the second case, then every S vertex has small common neighbor, but there may exist S minus 1 vertex in A with a large number of common neighbor. This leads to a clique whose size is close to the case 1. So we still don't know how to find a gap preserving reduction from subset intersection to clique. So next let's try dominating set. So let gamma G be the size of the minimal dominating set of the graph G. So we can ask a similar question. Can we find an FPT algorithm that on input a bipartite graph, we construct a graph G? If H has S vertex with large common neighbor, then the dominating set of G is smaller than G of K for some computable function G. And if every S vertex of A has small number of common neighbors, then the minimal dominating set of G is larger than 2 times G of K. So in this case, we succeed. And recently, Ija and I has showed that there is an FPT algorithm that from maximal K subset intersection to the dominating set that achieve a constant ratio for the dominating set problem. And so in particular, we construct a graph which is a C product of the bipartite graph H, and for every if there exists a S vertex with B common neighbor, then the minimal dominating set of G is less than 1 plus epsilon times d to the power of C for some constant C. And if every S vertex of A has a small number of common neighbors, then the dominating set of G is larger than C times d to the power of C over 3. And D is very huge. So immediately corollary of this reduction is we can root out a constant FPT approximation algorithm for dominating set for under FPT not equal to W1. And assuming ETH, we can improve the hardness ratio from constant to a slightly super constant, which is close to the first root of log of the size of the dominating set of G.
What is the running time?
You cannot
don't say under any running time, right?
The running time is FPT, parameterized by the size of dominating set of G.
That's the parameter, f of the parameter?
Gamma G is the parameter. And so gamma G is the size of the dominating set, and so it is the parameter. So let us not fail to mention the polynomial time in approximability of the dominating set. So we know that the hardness ratio for dominating set is close to log of n. And as far as the parameterized setting is concerned, not much is known. And for independent dominating set, we know it has no FPT approximation algorithm to any computable ratio function, and the FPT not equal to W2. However, the independent dominating set is not monotone, which means that if S is an independent dominating set, its superset may not be an independent dominating set. So we don't know how to find a gap-preserving reduction from independent dominating set to dominating set. So in the last part of
there is an old paper in I picked it on that one, the hardness of exactly the same problem, and we have also another archive paper on that.
No, I didn't. So I remember you have some result about dominating set and clique, but FPT in approximability result dominating set and clique, but you based on some non-standard hypothesis, like project game conjecture.
Yeah, but that's actually that one is not that non-standard.
Oh.
It's a standard.
Okay.
It's a standard.
Oh, okay.
Super exponential time.
Mm.
But in super exponential time, you cannot get better than log to the 1 plus epsilon, for example, for dominating set.
And this gap reducing thing, I mean, that was essentially in another paper that we have it 2 years in archives, essentially.
But will you rule out all the FPT algorithm for the dominating set?
Yeah, I mean, under some running time, essentially.
It's not
So-
FPT time.
But the running time of the algorithm depends on the ratio of the hardness ratio of the dominating set of the problem.
It's a big
So I need to check the paper later.
Yeah, you can check it later. Yeah. But I mean, there are some work done. It's not the case there's nothing done, essentially.
Okay.
And this gap reducing is exactly the same thing that we are using that in papers that are available like 2 years on, essentially.
So do you your reduction is based on PCP?
Yeah.
Oh. So in the last session, I want to show you the main idea of our gap-producing reduction. And so first, let us use the gamma x to denote the set of common neighbors of all the vertex in the set x. And our goal is to given a vertex graph G, and we want to construct a bipartite graph H in FPT such that if G contains a k-CLIQUE, then we can exist an S vertex set with large number of common neighbors, where H can be reduced to the case root of n. And otherwise, the common neighbor of every S vertex set of A is very small. So the key idea is to construct a bipartite graph T, whose left side is the vertex set of G. And it satisfies two nice properties. First, every k plus 1 vertex set of VG has a small number of common neighbors. And second, for random choose, k vertex set of V of G with high probability, it has a large number of common neighbors. So like this picture shows, the parameter k is equal to 3. So a k plus 1 vertex set has a small number of common neighbors, while for this 3 vertex set, both of them has a large number of common neighbors. And so the next step is to add the edge of G to the left side of this bipartite graph T. So if G contains a k-CLIQUE, then with high probability, this k vertex has a large number of common neighbors in this bipartite graph. And then we construct a graph H whose left side vertex set is the edge set of G. So if we have a k-CLIQUE with this number of neighbors, then its edge set here has this large number of common neighbors, and the edge number of a k-CLIQUE is equal to S. So in this direction, we are done. So suppose that G does not contain a k-CLIQUE, then every S edge from the edge set of G must use at least k plus 1 vertex. So like this case, and a 3 edge must use 4 vertex, and must use k plus 1 vertex. And in this bipartite graph T, k plus 1 vertex set has small number of common neighbors. So this is our reduction. It remains to show how to construct the bipartite graph T. So in this slides, I want to give you the intuition of the probability construction of T. So given so we construct bipartite random graph, and with every 2 vertex is joined by an edge with probability P, and the expected number of the common neighbors of a k plus 1 vertex subset is about 1, and the expected number of common neighbors of a k vertex subset of A is relatively large than that of k plus 1 vertex set. So I want to mention that our reduction can be de-randomized. So to that end, we need to define the bipartite graph T in a more sophisticated way. So by partition the left side of the bipartite graph T into an disjoint union of subset, and we keep the property T1 unchanged and replace the property T2 with this. So we want to for those k vertex set with large common neighbors, we want them to appear in a more predictable way, so that we can use it in our reduction. And it is not difficult to adapt our reduction to the bipartite graph T satisfying T1 and T2 prime. And the most technical thing is to construct such bipartite graph deterministic. Okay. In summary, we give an FPT gap producing reduction from k-CLIQUE to maximal k subset intersection, and under ETH we can rule out some moderate exponential time approximation algorithm for this problem, and we can even have a trade-off between the approximation ratio and the running time. And then we try to derive the inapproximability result of other natural parameter problem under this gap. And so far we can only rule out the constant FPT approximation for dominating set. And so it remains to be seen that if k-CLIQUE has a constant FPT approximation, or the dominating set have a FPT approximation with some computable ratio function.
Do you use a FPT is different than W1?
We can use FPTs different from W1. So if we use this,
because you got any time that you want. I mean, the T was not a problem. Did you use FPT is different is not W1?
It's not W1. You mean to obtain the hardness result for CLIQUE or for
anything?
Maybe you could go back to show the hardness result to see the step down.
So the first.
I guess we use it. The point is, use FPT is different from W1. We can only rule out constant in approximation.
I know that FPT, you can use the Exponential-Time hypothesis to prove that FPT is not W1.
Yeah.
Then you get any time that you want for free.
Any time for free.
And then it becomes only a matter of blowing the gap. Essentially.
So I didn't get how to blow. Blow the gap? Maybe I think you mean.
One is not equal FPT.
Yes, we use it.
Oh, yeah. Thank you very much.
But of course, this is a weaker statement than ETH.
But ETH implies.
No, it implies.
What? ETH implies W1 is not FPT.
Yeah.
And also W2 is not FPT. ETH implies this.
Yeah, for example, for under just ETH, we had this result that set cover means dominating.
Yeah, yes.
It is like you cannot get like a square root of log opt. That is a paper that we had in 2013.
What time? But you have got the cap on the time that you.
Yeah, we see that in certain time you cannot do that. But
yes,
that's
so arbitrary f here.
what was that?
There is arbitrary f of k in.
Yeah, that I know. But for all practical purposes, essentially that's the result that you want. That's a stronger result. I don't say. This aspect stronger, but we're bound by the stronger. But you should refer to this thing and don't say because we are using exactly the gap protection like 2013.
Lower bound.
Okay. I will check it later.
But I don't use it. You'll see what I mean.
You use a stronger assumption.
You'll see what I mean.
Okay, any more questions?
Actually, it's a related question. So your inapproximability result for dominating set is under the assumption that W1 is not equal to it.
Yes, we can use this assumption.
And where do you get this from? From reduction showing that you cannot solve dominating set in the law of k? Is that where you use it? Basically, in FPT.
Our reduction is from CLIQUE to dominating set.
From dominating set. So you show that
From CLIQUE to dominating set.
So you show that
Then
CLIQUE,
it's so much
if
harder.
dominating set is approximable, then CLIQUE is an FPT. Is that what you show?
Yes.
Yes.
Here k has nothing to do with anything because k is reduced beforehand to a very, very small function. And it has nothing to do with any optimum of anything. I'll talk about it.
So if there are no more questions, then thanks again.
Thank you.